Yeah, so welcome to part two. Let's discuss now just some special signals that we are going to encounter as we go through signals and systems and in general in engineering. The thing about it is that as we had in our block diagram yesterday, the model of the system that we're dealing with the signal coming into the system and going out, if that's the model, that's fine. But then in order to test the model, remember we were talking about it, in order to test the model, then what you have to do is to subject the model to all the possible signals that it is likely to encounter. Now that's very tedious. If you think about it, if you're designing an amplifier, let's say an audio amplifier, if you wanted to respond to the full frequency range that is supposed to be designed to, you're going to have to sit down with a signal generator, and you're going to have to send in all the frequencies from the lowest audio range to the highest audio range that the thing is expected to pass, and look at the output for each and every one of those, right? Of course, you spot check the frequencies and so on, but it's still very tedious. Or what do you call it? You're designing an industrial robot, for instance. The robot has to pick up an engine component from one place and spin around and put it on in another place. So you want to make sure that when you give it the command to pick up the engine from point A and put it on in point B, that it does exactly that and nothing more. And you have to cater for wrong signals. You have to cater for faulty signals and the like. So is there an alternative? Instead of having to put in every possible signal into our system, is there some other way we can test it without doing that? And these are where these special signals come in. Luckily for us, they occur repeatedly. And the thing about it is that by testing systems using these particular signals, you get enough information on the performance of the system to know how it will actually perform in the real world. So it saves you a lot of time. So the signals that we are dealing with here would be the continuous and discrete time versions of the unit step, the ramp, the sinusoid, and the impulse. And you would have met all of them already, but maybe not quite in the form that we're going to talk about shortly. As first off is the unit step. The unit step, of course, is a signal that is 0 before t equal to 0 and is 1 for t greater than or equal to. Now, this is a little, heavy side. This is a little issue here. Some mathematics books have it that t, they define the unit step, or somebody was saying heavy side function, t less than or equal to 0 and t greater than 0, right? Our case, we want the signal to change at t equal to 0. So once t is before 0, exactly up until 0.0, so a little epsilon time before 0, the signal is still 0. At 0, it actually changes, and a little bit after 0, it is now positive. We prefer that, and you'll see why shortly. But just to refresh yourself, where would you pick up something like this? Where are you likely to meet a signal looking like that? There you go. When you turn something on and off, that's a simple thing. When you turn something on and off, right? Before, if you look at this, forget the one here. No, it's not a pulse jar. We'll come to that in a little while. A pulse is different. If you look at it, this, and no, it's not a transient response. A transient response is what happens, and we will see that in a little while. That's an output. Remember, these are input. These are signals that are going in. Things like transient responses or so on are outputs, responses, okay? So you would encounter something like this. For instance, this behavior, not necessarily unit step, but this behavior happens when you turn something on after it has been off for a while. So exactly the point I was trying to make. In engineering circles, for instance, if I wanted to find out what a particular device was doing when I turned it on, the equivalent test for that is to put a unit step on it. It's on, it's off for some time, and then I turn it on. It goes from 0 to 1. It goes from 0 to 5 volts. It goes from 0 to 120 volts AC. You know? So turning it on and off, that is where practically you encounter the unit step. And just a little aside on Heaviside. I don't know if you were told this, but Oliver Heaviside was an electrical engineer. And his particular understanding, he was more of an engineer and less of a mathematician. So he understood how certain things worked, and he actually came up with the foundation of what subsequently became known as a Laplace transform. So he created it, but he couldn't prove why it worked. But he just knew that it did. So it allowed him to do certain manipulations at that point in time. And it's only after, a long time after, that the guy, Pierre Laplace, the French mathematician, actually proved what Oliver Heaviside figured out earlier on. Right? So electrical engineers have been in the middle of all of this thing from early on. And as is the rule, we kind of have to straddle the mathematics world and the practical engineering world sometimes, which is why it's important for you to understand sometimes how the mathematics works, right? Not necessarily to do it like how the mathematicians do it, but to know always if something makes sense or not. Okay, so back to what we're doing here. What happens if I multiply a continuous time signal by the unit step? Well, because the unit step is 0 before, for t less than 0, once I multiply the unit step by, once I multiply a signal by a unit step, then what happens is that all of the signal before time equal to 0, the signal multiplied by 0 is 0. So it basically chops off everything before 0. And the only thing that you have after 0 is a signal. 1 by the signal replicates the signal. All right. So every time you multiply a continuous time signal by the unit step, you basically remove everything that happened before t equal to 0. That particular thing creates something called a causal signal. In other words, the signal does not, causal signals do not exist before t equal to 0. Or maybe in a broader context, they don't exist until we start to look at them, right? Or we switch on the equipment, for instance. We like causal signals for exactly that reason. If you are making something or you have something working, the only way to figure out what it's doing is to have it start in front of you, and then you watch carefully what it does. If you meet the thing working, then you're not too sure exactly, well, how did it get there? Right? And without knowing how it get there, it's kind of difficult to predict what it's going to do next. So we, in engineering circles, we love causal signals. Right? There are signals that do not exist before t equal to 0. And t equal to 0 is generally you, the human being, your observation time. When did I start to look at this thing? And of course, we could do the manipulations like we spoke about before. I could delay the unit step, which is the one above. So that is u. And of course, the standard symbol for the unit step, of course, is t. ut minus t1 means that the unit step has been delayed by some time t1. ut plus t1, where I put the unit step here instead, right? So this would have been ut plus t1, right? And then the other one, this now we have taken t and replaced it by minus t. So what have I done? This is a time reversal. We just spoke about that. It's a time reversal. So this particular signal, I've replaced the t by minus t. So now what I've done is to flip the signal around exactly at the t equal to 0 axis. So the signal is now, sorry, not flip it around. I've reversed the signal. So instead of it going from, what do you call it? Is 0 before T1 and 1 after T1. It is now 1 before T1 and 0 after T1. Yeah? That is taking U, the expression for that one would have been U minus T. Oops. U minus T. So U minus T is the unit step. When the unit step doing this, that is U minus T. So U T minus T1 again is a delay. And if you want to figure out why is the delay, where is the U equal to 0? U at T equal to 0 is where? Right? U at T equal to 0 is at T1 equal to T. Here. T1 equal to 0, so it has moved that way along the time axis. Therefore, that is a delay. Yeah? Fair enough? Yeah. The discrete time unit step is a little bit different. The discrete time unit step are a series of values, right, at some interval of t seconds, t days, whatever the time interval happens to be. So it's a series of zeros up until t equal to 0, and then it's 1 every time at all the intervals after that. And the ramp. The ramp signal is a signal that, again, before t equal to 0 is nothing, and after t equal to 0, it's a 1-to-1. In this case, it's a 1-to-1 sort of slope. It goes up 1 unit in amplitude for every 1 second in time. And where would you likely encounter something like this? Think outside of it, and okay, not quite a transient, but think outside of electrical engineering. The behavior of something. Not quite. What about a vehicle under the speed of a vehicle under constant acceleration? You would find that the velocity going up constantly over a period of time. All right, now velocity and acceleration are things that modern cars would sense electronically to control. Right. So, for instance, again, in an electric vehicle, for instance, or in the anti-lock braking system in a car, it has to sense the velocity, and it also so that depending on what the velocity of the wheels are doing, it makes some sort of adjustment. So signals, those kind of sloping signals, they will tend to encounter when you're dealing with the distance, speed, velocity sort of changes. Right, and you get it by integrating the unit step. Right, if you integrate a unit step, the integral of a line is the integral of a horizontal line is a 1-to-1 slope. And of course, electronically, it's very easy to produce that. I believe you would have met an op-amp integrator, did you? When you did op-amps? Did you? Right, so you met an op-amp integrator and an op-amp differentiator. Right, they put a capacitor, depending on where the capacitor is located in the op-amp configuration, the signal that goes in is integrated and you get an integral coming out. So believe it or not, you can actually do a mathematical integration on a signal. Okay, so again, remember that sometimes we talking in mathematical concepts here, but the actual physical world can do some of these mathematics manipulations for us as well. And we talk about that when we do block diagrams. I'll mention that again, and how they put people on the moon with that. And the discrete time ramp, of course, again, it goes up 1 unit in amplitude for every time you sample it. Now the sinusoid, right? We spoke about that yesterday, a couple of things, and you know it. Omega is the frequency, phi is the phase, right? And phi is also a delay, right? Remember that phi. Oops, I'm having some issues here. Get my out. Right, so phi is a, forget that, whatever. Right, phi is a delay. Right, so you have it here, and you know it from, again, looking at the sinusoid. If you have the normal sinusoid, right, the normal sinusoid, if you have a delay on the sinusoid or a phase on it, it appears the sinusoid might look something like that. Right, and that is your this spacing here or this spacing here, wherever you want it, wherever the common crossing points are, that is your phase difference, which translates into, although you express it in radians, it translates into actual time because it's a function of time. Yeah. And of course, where the type of signal is encountered, you encounter it every time you plug a device into your wall. That's how our AC power grid looks like. It's a set of sinusoid. How long does the sinusoid repeat itself? That's a period. You know that. It's 1 over the frequency. And of course, this is the basis of the Fourier series and the Fourier transform that we'll come to. Right? And then we won't meet the discrete time version here. But if you ever stick around and you do another course with me, which is next semester in level 3, which is ECNG2011, we talk about discrete signal processing. And we use a discrete time sinusoid quite a bit in there. And now we get to the pulse. Somebody mentioned the pulse earlier in the conversation. So here's a pulse. A pulse, the graphic is a little bit skewed. The pulse actually is this part, right? The red part. Right? So the pulse from mod A less than A over 2, okay, which is here and here, PT is 0, and sorry, for mod A greater than or equal to A over 2, so here and here is less than 0, and for between these 2 points here, the amplitude is 1 over A. So what that means is that if the amplitude is 1 over A, it means the area under the pulse, which is the important thing, the area is equal to 1 unit. That's the important definition of it. Right? So not only that the width is A and the height is 1 over A and it's symmetrical about the 0 line. That's how we define the pulse. Now the thing about the pulse is, again, if you take our signal and you multiply it by a pulse, what happens? If you take the signal and you multiply it by a pulse, then because the pulse is like works like 2 unit steps. So everywhere the pulse is 0, it will get rid of the signal. And everywhere the pulse is 1, it would keep the value of the signal. So when you do that, you extract from the signal that before, you actually only pick out the piece of the signal between the time zone minus A over 2 and A. All right? And here we have the thing. What is the area under the product? Let's go and evaluate that a little bit. right? The area under the product is 1 over A. The function is 1 over A. Oops, let me go backwards. The function is, where am I? The function is 1 over A between minus A over 2 and A over 2. So if I ask you what's the area underneath the product, simple calculus is A over 2 between, you're integrating A over 2 and minus A over 2. GT, the 1 over A could take outside because that's a constant. The funny thing now is what happens as A goes to 0. If A goes to 0, as A gets smaller and smaller, both these limits here approach 0. Right? So this one goes to 0 from the positive side. This one is coming towards 0 from the positive side. This one is approaching 0 from the negative side. And if GT is continuous and it has a value at t equal to 0, then as this gets very small, then you're going to integrate the value just at the point where t equal to 0. Yeah? So in fancy language, which is what you would have learned way back when you were starting to do calculus, so mathematically now the limit of the area as A gets to 0, and basically what am I doing? When I say A gets to 0, what is that doing to the pulse? We go back to the pulse here, right? If A gets to 0, all I'm doing is saying that the pulse is now doing this. As A gets to 0, the pulse is starting to do this, right? Remember, the area has to be 1. So if the pulse gets narrower, the height is going to go up. Oops. The height is going to go up so that the area under the pulse remains 1. Yeah? Remember that. That's our definition, that the area of the pulse is also 1. So once we do that, so the limit of it is going to, as A gets small, it's going to eventually get so small that we're evaluating G at t equal to 0, and also this bit here. And we know by definition that is 1. So mathematically, the pulse, as we start to make the value of A smaller and smaller, eventually the pulse becomes the value of GT at t equal to 0. Yeah? Think about it. So if you go back here, right? As I make this smaller and smaller, what is happening here? As I said, this pulse is getting narrower and narrower, and eventually, at the extreme, we get a thing right here, right? The width is very, very close to 0, and the height is very, very close to 1 over 0, which is close to infinity. Yeah? But the important thing is that the area equal to 1. And the value picks out whatever GT is at t equal to 0. We call that the sifting property. When you sift out something, it means that you pick out a value from it. So the thing about it is that anytime you take a pulse, anytime you take a pulse whose width is very close to 0 and you multiply it by a function, then you pick out the value of the function at t equal to 0. And we call that the sifting property. It sifts out the value. And in our case now, we define that particular object, that particular function, as A goes to 0, the pulse becomes extremely narrow and extremely tall, but the area of the pulse remains 1. And we call that particular being a unit impulse. And we give it a special designation, which is delta t. So the unit impulse has infinite height and 0 width, which we know in the real world that can't exist, but we could We could fake it with electronics and electrical engineering. But the important thing is that it's defined. It's a mathematical definition. So if anybody asks you outside here, what is a unit impulse, right? Or what is the impulse function? The impulse function is not delta t equal to 1 or t equal to 0. Delta t is really defined by that circle here. It is a function whose area is 1. It's infinitely small, narrow, and it's infinitely small, tall. But it's in such a way that its area is defined as 1, and we call that a unit impulse. Yeah? Fair enough? So although in time to come, you'll forget that and you'll just simply say that the unit impulse is here, it's a pulse whose height is 1 delta t, etc. It really is just that really does exist for mathematical purposes. The definition of the impulse function is that integral there. Right, and that's why the mathematicians will, if you were to just put it down and don't put the integral next to it, they will take you up on that and say that you're not talking, you're not correct. And strictly speaking, delta 0 or delta t, which is the impulse at t equals to 0, is not defined because it's not defined as a function. It is defined as an area under the function. If you like, the energy of the function is 1. So it has a unit, it has an energy of 1, but it's not really a function because it's not defined at t equal to 0 in the strictest sense of the word because it doesn't exist. It's so small. But that's just for manipulation purposes. So back to our designation. So what is t minus t1? Delta t minus t1 is an impulse that is delayed or advanced. Delayed, right? So it's delayed by t1. So delta t, if you had it there, this was the original delta t, which means that t equal to 0. If you delay it, delta t minus t1 here, so this is delta t minus t1. All right? It's delayed. And delta t plus t1 would have sent the impulse on the other way. Yeah? And the other part of it is that you take any signal whatsoever, and you multiply it by the impulse. Remember, the impulse itself is this, right? The impulse is the integral and the delta part. So if you take a function and you multiply it by the impulse function, it picks out the value of the function at t equal to t1. In other words, it sifts the value. And that actually is a principle of sampling. You want a series of values at t equal to t1, t equal to t2, t equal to t3, and so on. So and we'll get to that. You multiply the signal by a series of impulses and you get the values coming out. It picks out those values. And what do you do if you integrate the impulse? Well, if you integrate the impulse between minus infinity and some point in time, remember the area, remember what the impulse is. The impulse has a value of, right? That's why we put a little arrow to show that it's infinitely tall. This thing has is defined as 1. So if I integrate it, in other words, what is the area of this thing? The area is 1. So if I plot the area is nothing before here, and then after here it is 1. So in other words, if I integrate this, I get this, which is my unit step. Yeah. And if you were to look at it in all, just like you have the evolution of man, we have the evolution of signal. So if you integrate the impulse, you get the unit step. And if you integrate the unit step, you get the ramp. And from there on, it doesn't matter if you integrate the ramp, you start to get nonlinear, you're going to get something in t squared. So in other words, you can actually go from one to the other, right? So you can start off, this one is right in the middle. So we were talking about generating these things in a practical term. If I have a unit step now, and I pass the unit step through an op-amp integrator, if I pass it through an op-amp integrator, I can create a ramp. If I pass it through an op-amp differentiator, I will get an approximation of an impulse, because it depends, of course, it can't get infinite height. The op-amp will only go as far as the power supplies will let it go, but you will get a signal, you will get an impulse right at time zero. So electronically, it's possible to create all of these with a unit step. And a unit step is just simply, you start, turn on the circuit, and there it is. So you supply, for your op-amp circuit, you supply a voltage, you have nothing, you turn on the voltage, and then at the output of that, you're going to get a ramp. Or if it was a differentiator, what's going to happen is that you're going to get a pulse, which is as close as it could give you to an impulse. Yeah? So it's all possible to do those things electronically as well. So questions? Yes, Jama.
Hi, sir. I have two questions. I saw that on one of these slides, you had something, a symbol E. I don't know if I missed it while you were speaking, but what did you say it was?
Right. So when we were doing the integration, let's go back a little bit. Good. When we were doing this, we said what happens to the limit as a gets to 0. So in other words, what is going to happen is that if a gets to 0, this here is going to approach 0. Similarly, this limit here is going to approach 0 as well. So mathematically, what we do, because I can't integrate, if I have an integral between 0 and 0, I can't do anything. So to evaluate it, we let it get as infinitesimally or very, very close to 0, and we use a little symbol, which is epsilon. So the upper limit, as it approaches 0, will be just slightly positive, because remember, a over 2 is a positive number. So it gets very, very small. It's approaching 0, so it's a very, very small positive number. And similarly, this one is going to become a very small, very, very small negative number. And we use the symbol epsilon. It's a standard notation for us, that epsilon is what we use to represent very small deviations and numbers. Yeah?
Okay, thank you, sir.
And what's the other question? You said you had another question, I believe.
Okay, so okay, I understand that you said that the pulse area would be 1, but I'm not sure why it is 1. Could you go over that, please?
Right, because of how we define it. Right. We define it like that. Remember, we say that the pulse has a height, and that was our choice. The pulse's height is 1 over A, and the width is A, right? The width is A. So what is the area of that pulse? 1 over A by A, which is 1. So we started off by a definition. We are defining a pulse whose area is 1. And then what we do is that we start to make A smaller. So it's going to do this. If A is smaller, 1 over A is going to increase. And the width here has to get smaller. But the area underneath still remains 1. Yeah? And then we keep doing that We keep doing that. We decrease A again. Yeah. And the area here is still 1, but it's getting taller and it's getting narrower. And we now look at the limit as we make A very big. So 1 over A gets extremely small, and 1 over A gets very tall, and A gets very small. But the product of 1 over A multiplied by A is still 1. And in the absolute limit mathematically, it approaches 0. But of course, 0 by infinity is undefined. So we take a little, we step back a little way, and we say, okay, it's not quite 0. It's a little epsilon, which is very, very, very close to 0, but still something we could use. Yeah?
Yes, sir. Thank you.
So the definition can change if the height changes. No, the definition, the area is still 1. Remember, what we're doing is as the area is 1 over A by A. Remember, the area is 1 over A multiplied by A. So if this changes, it's changing here, it actually mathematically cancels all the time. Right? So regardless, once I change A all the way through, it doesn't matter, the answer is still 1. But I'm trying to make it in such a way where A gets so small, so that actually what we have is this function right on t equal to 0. Yeah? Any other questions? Yeah? All right. Well, you have the handouts. So let me stop the recording here for the time being.